Okay guys, this video is going to be the first in a series of videos covering Chapter 8 of the textbook, which deals with advanced theories of covalent bonding. In this chapter we're going to talk about two theories. One is the valence bond theory, which we'll get started with in this video. In the next video, part of valence bond theory involves what are called hybrid atomic orbitals. And we'll also discuss multiple bonds in that context. And then the second theory that we'll look at, which is distinct from the valence bond theory, is called molecular orbital theory. So we'll save that for later. The picture that you see here is kind of an interesting one. What you're looking at is liquid oxygen. Okay, and so here someone's pouring the liquid oxygen between two magnets. And it turns out that oxygen is a paramagnetic molecule, which means it's susceptible to the influence of a magnetic field. And it turns out that the molecular orbital theory is probably is a theory that predicts that molecular oxygen is paramagnetic. And so that's one of the success stories of molecular orbital theory. And we'll get to that in a future video. Right now we're going to start with the valence bond theory. The main idea of valence bond theory is that covalent bonds in a molecule are due to the overlap of atomic orbitals. And we are going to talk about different types of bonds within the valence bond theory, so-called sigma bonds and pi bonds. So, as I said, the main idea is that in order to have a chemical bond between two atoms, the atomic orbitals of those two atoms must overlap in space. Okay? And the more overlap you have, the stronger the bond that forms. Okay? So this enables electrons to be shared between two atoms. On the figure on the left here, what we're looking at is an energy profile for diatomic hydrogen. And it's showing us a representation of the 1s orbital on each hydrogen atom. So it's this sort of cloud here that represents the wave function for a 1s electron. And each hydrogen atom has one 1s electron. And as you bring the two hydrogen atoms closer and closer together, the atomic orbitals of the two atoms start to overlap in space. And at a certain point, you have very good overlap between the two atomic orbitals, which leads to electrons being shared between the two atoms. You can see that results in the energy being lowered, which means that the diatom is more stable than the two separated hydrogen atoms. And that's what we get for the covalent bond. Okay, so this bond, this length here, this distance between the two hydrogen atoms, this is the bond length, the equilibrium bond length for H2. Well, if you try to put the atoms on top of one another, you get repulsive interactions between the nuclei, and so the energy goes up, and then the molecule becomes unstable if the bond length is too small. But you get the idea here. And so the main idea is that you have to have good overlap between two atomic orbitals on different atoms in order to have a bond between the two atoms. There's different ways you can do that. So this diagram involving H2 shows you the overlap between two s orbitals. Here we're looking at an orientation dependence for the overlap between p-type orbitals. So here this dot represents one nuclear center, this dot represents another nuclear center, and so we have two p orbitals, okay? And in this configuration, with the p orbitals oriented towards one another, you have good overlap between the two atoms, but at a different angle. So if the p orbitals were pointed in this direction, you would have not as good overlap. So there is an orientation dependence to the atomic overlap, which leads to specific directions in terms of chemical bonds. And we're going to see some examples of that in the next couple of videos. Here we are going to classify chemical bonds according to two different types by their shape. Sigma bonds have a so-called circular symmetry about the bond axis. So in this bond that's formed between two s-type orbitals, if you imagine looking down the bond axis, okay, so if you put your eye in this direction and look down that direction, there would be a circular symmetry to the overlap. Okay? And so this type of bond is classified as a sigma type bond. It has this circular symmetry. In panel B, here we're showing the overlap between an s orbital on one atom and a p-type orbital on another. Okay? And in this fashion, when you look down the bond axis, again, you're going to have a circular symmetry to this overlap. Okay? You could call it a cylindrical symmetry, if you will, as well. So this is also a sigma type of bond. Here, the overlap of two p orbitals also has that cylindrical symmetry, that circular symmetry about the bond axis. And so this is also a sigma type of bond. However, if you were to turn the two p orbitals 90 degrees, you would no longer have that circular symmetry. So here's a distinct type of bonding pattern. So here's the two nuclei, the two dots, and then you got the p orbitals, one's pointing up this way and the other one is parallel to that, it's pointed up that direction. You can see that you've got good overlap above the bond axis and below the bond axis, but there's nothing in between. There's a nodal plane that runs through the bond axis. This type of bonding arrangement we call a pi bond. Okay? And so it does not have that circular symmetry. In fact, it has kind of an inversion symmetry. That is, you go from one phase of the wave function above to a different phase below. Anyway, this is the pi type. Single bonds, we've talked about those before, those are always sigma type. Okay? So whenever you have a Lewis structure that has a sigma bond, like this one for hydrogen chloride, that single bond is a sigma type bond. When you have multiple bonds, for example, this double bond involving diatomic oxygen, one of the bonds is sigma type and the other one is pi type. Okay? So in every multiple bond, there is one sigma type bond, and then the other bonds are pi type. Okay? So in diatomic O2, we have one sigma bond and one pi bond. In diatomic nitrogen, there's a triple bond, and the first bond is a single type, okay, sigma, and then the other two bonds which make up the triple bond, those are pi type bonds. Okay, so one thing we need to be able to do is to count up the number of sigma type and the number of pi type bonds in a molecule. So in this example, they want us to look at butadiene, and I'm going to go ahead. You're not expected to know how to draw the structure for butadiene in this course. I'm going to go ahead and draw the structure. Butadiene has two double bonds and one sigma bond between the carbon atoms. And then there's also bonds, there's also single bonds to the hydrogen atoms. So what we want to do is count up the number of sigma and pi type bonds. Each of these single bonds is also a sigma type bond. So each carbon-hydrogen bond is a sigma type. And then when you have a single bond between two carbon atoms, that's also sigma type. So there's a sigma bond there. And then in these double bonds, one of them is sigma, and then the other one will be pi for each of them. Okay, so let's count up the sigma. There's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. I count 9 sigma bonds. Now let's count up the pi bonds, 1 and 2. So 2 pi bonds. I want you to look for examples of this in the end of chapter problems of the textbook to get some additional practice counting up sigma and pi bonds. Well, I'm going to go ahead and stop this video here. The next section is somewhat long, so we're going to make this video short so that we don't have too long of a video.